would like to kind of pass this over to Chris Banton, who's going to talk a little about our sponsor today and introduce our speaker. So, Chris?
To introduce Orlen. Orlen has been in this industry for a while. It's certainly a valuable resource for me to ask any questions, and he's just a tome of knowledge around PCB design and anything with printed wire PWBs. So he's got just tons of knowledge around PCB design, DFM knowledge, manufacturing, and there's a regular speaker and teacher for us, and he always gets high marks for his ability to explain all these things and keep and help our customers be better at their craft. So with that, I'll kick it over to Orlen and take it away. Thanks, Orlen.
Thanks, Chris. Welcome, everyone. We're going to talk about RF designs. I can remember back when I was hand taping boards, the RF engineer told me that RF designs were the wave of the future. We've been in the future for some time now. So we're going to talk about what are RF waves, the best practices to use when designing for the RF signals, common RF design pitfalls and how to avoid them, questions you should ask when you're working with an RF circuit. These questions not only come from the RF engineer, but also your fabricator. Strategies to mitigate RF signals from the RF simulator to the CAD tool. And then we're going to take a look at the InspectAR. So the radio frequency, RF, is the acronym. It's the rate of oscillation of the electronic magnetic wave in the range of 3 kilohertz to 300 gigahertz, as well as the alternating current carrying the radio signal. This is the frequency band that is used for communicating transmission and broadcasting of the signal. The Wi-Fi, the energy field that is transmitted as a wave. The distance between a Wi-Fi wave is shorter than that of a radio wave, but longer than the microwave, giving the Wi-Fi a unique transmission band that can't be interrupted by other signals. The microwave, a reference of a class of waves, microwave range, or is a spectral range of the frequency for the Wi-Fi signal operates. There's our range, as you can see in the slide below, from the radio wave to the microwave, all the way up to gamma ray. The examples are your laptop. It's transmitting at 2.4 gigahertz, the frequency found within the microwave range, or the spectrum of 300 megahertz to 300 gigahertz. So best practices when using and designing RF signals. Ground, RF ground, and I'll say it again, RF ground. That's going to be your best friend. The component selection for RF should be surface mount. That's not always the case. We have to use through holes sometimes, but in all cases, if possible, surface mount is the best use. You're limiting that signal to that top layer or bottom layer that the RF signals are on and the components are on. The RF components that are created out of copper, they're actually components out of etch that you've created, should be gold plated, should not be solder mask covered also. The use of the multi-layer PCB is best. That's going to give you the ability to go ahead and put that ground plane down in there. The power plane should be included between, preferably, two RF ground signals. That would be grounding and keeping that power. Most of the power shapes are broken up, so you'll have multiple power shapes in there, and you really want to shield that. The RF signal lines and RF components. The bottom layer, if you're going to be just a two-layer, the bottom layer should be the RF ground on there. And that would be your shielding that you're looking for on a two-layer board. Two-layer board is not ideal, but in some products, it is. The best practices, as you use the least amount of vias in RF routing and the maximum number of vias when we're doing our grounding. If we're using that multi-layer PCB to route the short RF grounds on the top, we want to reduce the noise created by the power shapes, maybe split planes on those power shapes, and we sandwich those between the two ground planes. There must be absolutely the ground plane under the layer of the RF signals. We need to shield that. The connection for the ground pins to the RF components to that RF ground plane as short as possible. VN pad is the best use of that. If you can put VN pad, you couldn't get any better than that on your signal. That's a cost adder, VN pad, but with your RF design, in most cases, it offsets that for a working product. You should use multiple vias to reduce the unwanted effects of that ground. So multiple ground vias is a must. So you have to use through-hole components and vias that might be going all the way through the board. In this case, we want to do some back drilling. We want to get rid of that unwanted antenna. And what we're showing here in this diagram is the signal's flowing as a normal signal flow, and the rest is really a distortion to that signal because it becomes an antenna out there. We want to back drill and alleviate that antenna in there. If you're doing a coral design or a planar, they generate a very strong magnetic field. Place them and isolate them from all other parts to prevent any interaction and noise coming off of those devices. This includes purchase components, not only the etch that you create copper on the board. So the coil or planar components is best used as purchase parts, but can be used as actual RF copper that you're going to actually print down on the board material. Best practices when we're in there routing. The proper cornering. Good is either the 45 or arc. Better yet would be the angle that you'll put in there. The best is to go in there and calculate that. The nice thing about it is the software will go ahead and calculate that. Diagram on the right shows that I want to go in there, and I can decide if I want it to be mitered, if I wanted unmitered or to curve, and then I'm going to put my working frequency in there in gigahertz, and then it's going to go ahead and do the calculation. If I'm routing for the best optimal way to do it would be the best, where we're going to actually do the miter, and then the software is going to go ahead and do that calculation for us. Great improvement over the days of hand taping. There are times when an RF fence is required. We're isolating signals, RF signals within the entire RF design, and we'll do that either with a fence or we'll do a complete frame chassis that would set over the board and bolt down onto the board. That fencing or that frame is going to have an isolation in there. We create what we call mouse holes that lets the signal leave that area, and that's a controlled signal going to another section of the RF board. And there are times where we do a complete cover over the design, metal frame on that. Some applications, they'll do conformal coating on that, but in most cases, the metal shield is the best in there. So we need to respect the wave. So a wave is the distance between two successive crests or troughs of the wave. The wave is the distance from one crest to another, or from one trough to another. It is on a electromagnetic wave. It can be on a sound wave or any other wave. It reminds me of my college days when I was asked a question, and I think the question was to provoke us to think, but if you're out in the woods and a tree falls, does it make a noise? Most would say no, because they weren't there to receive the noise. I always felt that sound wave was created, whether or not I was there to receive it or not, didn't eliminate the sound wave, it was there. So apply that thought to RF. Just because you don't have the equipment to realize that that signal's there or that noise is involved in your signal doesn't mean it's not there. You just might not have the equipment to be able to tune in and understand that. And then the frequency, it's really the number of waves that pass through a certain point on a specified amount of time, whether it be the trough or the crest. And the low point of the wave, of course, is the trough, and the distance between the two successive peaks, or as I indicated before, the crown on those. So that crest is what's important. So the ground, I ground both ends of any copper pour, and I stitch as many vias whenever possible. If I had the freedom to go in there and use blind and buried vias, I will actually put ground vias at different levels throughout the design. So I could go from top to my RF ground right underneath the top, and I could stitch vias from 1 to 2. That's not to say later on I wouldn't stitch a via from 2 to 4, depending on the stack up and how it is. But you cannot put too many vias in there. No copper islands should be near any RF signals. Basically what you're doing is putting some antennas out there. So do not use copper thieving near the RF circuitry. If a board house comes back to you and asks you to put copper thieving in there, then what you should do is already have ground fill, the RF ground fill back in there. Any area that would require copper thieving would be a good area to go ahead and backfill with ground and put as many vias in there as you can. The board house won't have any problem with the warpage or the lack of copper in that area. The only time that is not true is, of course, an antenna design. You do not want to have copper underneath that antenna. That might be the only place, and that's such a small area, it should not affect the fabrication at all. If the board includes multi-layer ground planes, provide as many of those vias as you can. As I was saying, I'll go from 1 to 2, I'll go from 2 to 4, or wherever the signal traces will make a transition from one side of a signal through the plane to another side. Immediately have as many ground vias as you can at that signal. Keep those trace lengths to a minimum, and start your layout with the most critical circuits and as close to the devices as possible. The diagram below is showing that I can automatically put thieving in there. That is a mistake with the RF circuitry area. Although the tool allows you to do that, you can also backfill with ground just as easy with that. Common RF design pitfalls is that we be sure that the models that you're doing has the inductance of the via for those sensitive traces. Again, the ideal thing is no vias, but if vias are there, be sure to model that inductance of that via for that signal. Use the isolated vias to separate portions of a filter or a matching circuit. Again, some of those matching circuits might need a fence or a frame put around them to shield them. Note that the thinner PCBs do reduce the influence of the parasitic inductance in those vias. The thicker boards, back drilling is needed, or if money allows, blind and buried vias is the way to go. Remember, if you're doing that back drilling, they got to knock that pad out, so they're going to drill it even larger. Now it becomes a new spacing requirement in there as you back drill, because you're drilling that pad out, you're using a larger drill to knock that pad out. A lot of people will forget that I need that extra spacing because I'm going to do some back drilling. Avoid the use of the planar trace inductance. I have that as the middle diagram. Our tool will allow you to create these planars and coils automatically. In there, you can set the windings up, whether you want round, the rectangle, octagon, hexagon. Ideally, buy a component. What you're doing with the component that you purchase is you're able to shield that better. The inductance in that copper can cross over to other signals, so shielding is very important versus the wire wound inductor that you see on the far left. Other pitfalls you might find is the short traces between the crystal and the RF device. So we got a crystal in there, we got an RF device. I keep the interconnect traces separated as much as possible. And if you suspect excessive shunt capacitance, vacate that ground plane underneath your crystal. That would be on layer 2. Avoid providing continuous grounds under those traces. Don't avoid, I'm sorry. Always provide, don't avoid, always provide continuous ground under those traces. Again, unless the crystal is causing problems there. Orient the sensitive traces orthogonal. If the traces must be run in parallel, you want to ensure adequate separation, or you want to actually do a shielding of those traces. The diagram in the bottom left shows the shielding of RF connectors. The software will automatically go in, identify that trace, and create that shielding for you. The software also will go in and fill that shielding in with the RF ground vias. The diagram in the upper right corner shows the way not to design with the crystal. Here's what they've done. They put the RF device, let's say on the top, that's your blue, on the bottom's your red. And what they've done is they put the crystal on the bottom. They're routing out of that into the capacitors. That's good, except for the fact now you're going through a via, so you're adding inductance there. It'd be better to make room on the top for that. Come right out of there. I would not lay those down in a horizontal position. I would have C5 and C6 rotated in a horizontal or vertical, not horizontal, so that when I come out of there, notice that the C5 on the right, after it's coming out of the crystal, is now trying to go down between C6. And again, we're hitting that via, and that's not ideal. I can take that circuit and relay that out, and you will never have a problem with that crystal on there. The other thing that you'll notice is we're not seeing a ground plane underneath that crystal, and we're seeing other circuitry. So underneath there, of course, the crystal's on the bottom, but underneath that would be looking at the top, and they're routing regular signals through there. I would not do that. I would avoid that, putting any of those traces in there. You're asking for trouble on them signals by doing this. Questions you should ask when you're working on a RF circuit is health and safety requirements, commercial products, your microwave oven, our cell phones. Notice the number of different shielding little panels that they've created to shield. Notice the shield is removed from the one device, but underneath that shield, as you see the diagram, there is still a framing separating two sections in there. That's your cell phone technology is really requiring that for the type of signals that we're running with the cell phone. That shielding is very important, whether you're doing it with a frame and a cover on there. Product life expectancy. You want to make sure you're designing to last your product life. The shuttle program was supposed to be 25 years. We stopped short, I think 10 years short of total life expectancy on the shuttle program. When I started out, the International Space Station was just an idea. I was working at GE Aerospace. Valley Forge, Pennsylvania had a prototype. We were going to design the International Space Station. The project I worked on got a lot of jokes thrown at it because it was the toilet that wouldn't flush. Our plumbing today relies on gravity. I think everyone realizes that. We didn't have gravity up there. That was a milestone to overcome. Since then, of course, we have SpaceX, and the shuttle's been retired. Space station has grown in size. My latest project, one that's a little more enjoyable to talk about, was the Polar project. The Polar project was taking specimens up to the space station, frozen. So we had to maintain minus 115 degrees Fahrenheit on that, frozen units. The first ones were brought in. I worked on that project. The three things that impressed NASA the most was it was on time. That's rare. There was no cost overruns. That's another rare thing. And third, no repairs. And it's been up there since 2015. It's been in operation for 6 years. They've moved from one unit now, there's 6 units of that freezer unit up there. And the joke that I laughed about when the comment was made that if you remember, they sent ice cream up for the astronauts. and someone made a comment and said, I heard they had ice cream in your freezer unit. And of course, being the way I am, my first response, that's what it wasn't designed to do that. we were to take specimens up there. We were not to go up there and send ice cream, but you know, I mean, they are isolated up there. They have to have some enjoyment. The SpaceX capsule, cargo capsule, is what delivered that unit up there, and they still will use that. The reason there's 6 up there, we will keep specimens up there, and then we have to transport back when they're done testing and refreeze those units and bring them back down. And they literally bring the polar unit with that when it returns to Earth. So we need to look at the stack up. It's very important of the stack up. As you can see here, I've got this board here was framed off with different sections. There'll be a frame that snaps up over top of this and a metal shield. Materials used in that stack up is very important. So the fact that we do not want any of our signals necessarily oscillating out. So the material selection, FR4, the plain FR4 is not really good for RF designs on there. With that said though, the key place to work with is definitely your board fabricator. Be in close contact with those people. Let them know what the product's being used for. If you're aware, there's 3 product ranges, a class 1, class 2, and class 3 product. The class 1 products might be the remote control to open your garage door. So think about you're at the end of your driveway and you're using your remote control to open that garage door. Notice though, over time that the signal gets weaker and you got to get closer and closer to the garage door to open it. What happens there is the signal's not being propagated out properly. What happens is you need to change the battery, needs more power. So there's a case where that's a class 1 product. If it fails, you know, you throw it away and you get a new one. Class 2 products usually are in medical, or at least costed enough that you want to go in there and change those. In those materials, it costs more to just throw that away and replace it. So you want to rework it or at least find out what's happening. Now we get to the class 3 product. Class 3 products is usually military and a lot of medical equipment. And in the class 3 product, many people I've taught will hear me say that the best you can hope for in a failure of a class 3 product is a body bag to send home to the family members. And Boeing has experienced that with their MAX jet. That was a class 3 product failure. There was not body bags to send home to family members. So be aware of what product you're designing. Make that known to your fabricator. They are full understanding of what you'll need as far as materials and stuff. So the strategy to mitigate the RF circuit from the simulator tool to our CAD tool. So the OrCAD PCB input allows for DXF or IDFF. The Allegro PCB RF option gives you a IFF bidirectional, so you can go either way, in or out. So how do I get my OrCAD PCB back into the simulator? I can do it with a DXF, or I can do it with Gerber files. And that's how I would get those in there. There are more than 3. I list 3 top simulation tools. Number 1's AWR. I list that. That's the first one I ever worked with, Microwave Office. Done a lot of designs and worked with RF engineers using the Microwave Office. The little diagram shows they're into system design, circuit design, simulation, of course, layout. They're trying to do the full gamut of everything in there. And I find out later that Cadence are part of the Cadence family, and we're looking at doing a better migration from Microwave Office into both OrCAD and the Allegro products. And of course, the other 2 are listed there also, just to be aware. The whole idea, though, is really to simulate long before you ever fabricate. In the days of the hand taping that I talked about, I can remember having to trim off a little of the tape, create a new board. We'd go out, we'd try the board out, come back, cut off a little more, fabricate another board. I mean, it was very trial and error back then. with the software, we've made tremendous strides toward simulation. You can really almost do a one-turn RF board nowadays without any problem, but we're not going to be able to do that without the simulator. You need to simulate that. And then we want to go ahead and talk about the InspectAR. We wanted to fit this in. This is CAD neutral, so it doesn't really matter what CAD system you have, but it will turn your mobile phone or an external webcam into an intelligent viewer. So I can go in there and I can ask it to, at least show me areas that I want to be concerned with. I want to look at certain power planes, certain traces in there that I'm doing, effective collaboration on there. And for those military installations, you can use this tool and not go out to your mobile phone, of course, which would probably not be secure, and you're not going to be allowed to do that anyway. Most of the locations I've showed up at, they take my mobile phone away from me before I go in and scan my computer. So, but this tool we do have it set up so you can use it in those type of environments. Basically, you're having an external webcam set up, and you're just in the facility there using the tool that way. There's a free trial. You can see the link down below. Yeah, you'll get information for that to sign up for a free trial. All right, so here's one of my typical designs. We'll zoom into just this area here, and I want a little tighter zoom in there. So what I want to do is go in, again, it's an RF option on here, and I want to go ahead and I'm going to add my connect lines in here. And I will go over to the options, and there's my options in here. I do want to change this to 15, not, oops, 15 in there. We're working frequency 7. I will connect on to that pin, and I'll come out. Notice I'm in the arc mode. I'll lock in that first one. This first one takes a while. What it's doing is it's opening up this shape, and then it's following my constraint rules I've set up with it. And then it will put my components, its actual components that it's creating as it goes. And then it'll put that component in, and then I can go right on up here and make my connection. So what I can do then, I'm done with that. I can come back with the RF, and now I can do a conversion, and I want to take these components I put in and convert them over to a shape. So I'll go ahead and select those and get the shapes done. And then at that point, I can come back to the basic commands of shape and do my merge. And I can literally merge my shapes together. I guess I didn't do a full conversion. Convert component to shape. I'm not getting it to report back that it converted it, but let's try one more time. Amazing in these live demos. I run this a couple of times this morning, no problems whatsoever. Let's merge those, merge that. There we go. Now notice that it's one continuous shape in here. I now can come back and convert it back to a component. So under the conversion, I can now take the shape and now make it a component. Now I can use this component again. You notice that I have some components that I've created out here. They're here if I need to duplicate the circuit that I'm coming at. I can have the shape already there. Again, it's a component, but I can create it first as a component when you're running the etch, and then kind of convert that into one continuous shape, and then convert it back to an RF component. Again, RF component, copper, basically just a copper on there. Gold plating is definitely ideal in the case of RF circuits. So there we are. I'll go back to Brianna. Thank you.
Okay, you can hear me, I suppose, and see me?
Yep.
Okay, good.
Well, we can't see you, but I can hear you.
Well, yeah, that's what I mean. You can see my screen.
Yeah.
Anyway, Orlen, great job. Thank you for all the information and the questions and answers. Was pretty interesting. So we're ahead of the game. I do want to do a little wrap up here. I want to thank everybody who attended, and special thanks to EMA, our Design Automation, the folks that hosted the webinar here for us today for our chapter. I do want to encourage people to join the PCEA. If you're local to Southern California, we'd love to have you in our Orange County chapter. It's going to be virtual until we can go places again. And there are other chapters in the country as well as virtual chapters. And so please go to the PCEA website that's listed below there. And, remember, collaborate, educate, and inspire. And if you have any other questions or something that you want to reach out to me, there's my email address. And again, we hope to add members. What I will do is I will be sending information to everybody who attended. We'll get the link to where this ends up on the YouTube, so you'll be able to see this. We'll thin it down. You won't have some of the baloney here at the end, and at the beginning you'll get the real technical stuff in there. And also I will send along some flyers and information about that educational stuff that we talked about. And for those people that are interested, we're very excited about it. It's just you just don't get that kind of stuff in any other form that's going to be this advanced. So anyway, I guess we will sign off. Thank everybody for coming again, and have a great day.
Thank you.
Wait a minute!